Let's review everything we've learned about how to simplify radical expressions. So expressions that contain radicals. Now, let's first note that I'm not talking about an expression that contains rational exponents like this. Even though, yes, we know that by definition, that kind of underlying these terms here are radicals. You know, x to the 4/3 would be, you can write that as the principal third root of x to the 4th. Let's just start off by thinking about if we had an expression that contained radicals, and for the most part we were going to stick with the radicals. How do we simplify it? What have we learned about how to simplify radical expressions? But at the end of this video, we'll come back to how, you know, these are kind of the same, you know, type of equation. So how are these mixed? We'll come back to this at the end of the video. Okay, so to simplify a radical expression, we use the properties of radicals. These here. So like the product property, the nth principal root of a times the nth principal root of b is the principal nth root of a times b. Same thing with the quotient property. But the indexes have to be the same for these properties, but for the nested radical property, they don't. The principal mth root of the principal nth root of a is you can write that as the principal m times nth root of a. Okay. Now, when it comes to simplifying radicals, it can get a little bit tricky, in particular because of this first property here. So if you have the principal nth root of a to the n, okay, well, if n happens to be even, then we can't just, so we would, in general, when you look at this, you might think, well, okay, convert this to the exponent form, right? Well, n divided by n is 1, okay, so this is just a. And if n is odd, then this is true, no problem. If you had like something like this, well, then this would be -5. But if this was +5, it would be +5, so it's just a. However, if n happens to be odd, or if n happens to be even, then this needs to be the absolute value of a. Because you wouldn't want to say, if you had this, you don't want to say -5. That's not correct. You want to say this, right? And so this can get a little bit confusing when you're trying to simplify a general radical expression. Like, how does this property here come into play? If n is even, then the principal nth root of a to the n is the absolute value of a. Okay, and so we'll talk about that in a second. But with these properties, okay, you use these properties to simplify radical expressions, and the general idea with a radical expression was that you could identify 4 different points that would indicate that a radical expression is not fully simplified. For any radical expression, if you have any of these 4 cases, then it's not done being simplified. Okay, and so the first case is the one that we're very familiar with, and it's the idea of, so if you have a like x to the 7th, the principal 4th root. Well, since this power here is greater than or equal to the index, well, then it's not fully simplified. We know that we'll be able to take out one or more of these perfect 4th powers of x. Okay, so now, but where does this, how are we able to do this? Well, this comes from the product property. This comes directly from the product property. The nth root of a times the nth root of b is equal to the nth root of a times b. We use that in reverse here. So we know that we can write this as x to the 4th times x cubed. Okay, now using the product property in reverse, we've got okay, and then now we can simplify this. We can turn this into, but this we can't simplify, but we can simplify this. Now, but here we go. Here is we've got the nth root of a to the n, or x to the n, when n is even. So, okay, we know this is the absolute value, right? So is that it? Are we done? Is that correct? Well, no, actually, this is not correct, because we don't need the absolute value in this case. And this is where it gets kind of confusing. You might be saying, well, why not? This is exactly what it said in this property here. The nth root of a to the n when n is even is the absolute value of a. That is exactly what this is, except where a is x. Okay, this is what you have to think about. When you're simplifying a radical expression, go back to the original expression. Like when you're first starting, look at the original expression, and you want to think about, okay, like what in this case, what x values am I allowed to input here? Because we know you can't have with a even index, you can't have a negative in the radicand. Well, okay, this is x to the 7th, an odd power, so x can't be negative here. X can't be negative to start with. You want to think about this. It's like a computer program, or something like in Excel or whatnot. You would only allow certain inputs, whoever to input only certain numbers. You couldn't, if they inputted an x, you couldn't simplify this. Like this property here, this property, the product property, it doesn't apply if you have a negative in the radicand, because then the radical doesn't even exist anyway. Like these properties here, these properties do not apply if you happen to have like a negative value inside of an even index radical, because then you don't even have it doesn't even exist in the first place. So going into this, we can see x has to be positive. So in that case, if x is positive, you don't need this absolute value. You just do that and you're done. Okay, now what about if we had something like this instead? Well, what happens here is you look at this and you say, okay, well, x can be, you could have any input here. You can input any x here and it's completely fine. Like if this was a program in MATLAB or Excel you were making, you could input any x and it's fine. Because like -5 to the 10th is going to be even, or is going to be positive, and then you can have a positive inside of the 4th root radical, so that's fine, right? Okay, so let's do x to the 4th. Okay, so using the product property, okay, now since x can be negative, we have to do this for sure for each of these. And the reason is, if you think about it like a computer program, it's because if someone inputted an x, they can input a negative x value, right? But whenever you go to return the answer, you would say, okay, well, just output what the person inputted. That's what x is. Well, then if you didn't have the absolute value, it could come out as negative. That's not correct. You're never going to have a negative value come out of a principal 4th root, principal even root. You'll never have that coming out. That would make no sense to have any negative values coming out of this in any way. So you have to have this absolute value. However, this is a special case that since we happen to have 2 of these, we actually can just do, we don't actually not going to need the absolute value anyway. Just because it just worked out that we had 2 of these. Because you could think about it, someone inputs an x, right? Now you output just an x as well, and so let's say it's negative, but then you're multiplying it by itself anyway, so you square it, it doesn't matter anyway. If it happened to be the case where, let's say this was x to the 14th, then you'd have 3 of these principal 4th roots of x to the 4th, and then you'd be left with this. Well, then in that case, you'd have 3 of these absolute value of x. Then you would need to leave it like it is, and you could simplify that this way or this way, however you want. And then with the x cubed, this 4th root of x squared on the end. Okay, and that's going to be the general idea of how you're going to analyze any radical. So like, let's do an example with multiple variables here. Okay, well, you're just going to, when you start, you just look at this like, what am I allowed to input for C and D? C can be anything. C can be anything because you're raising it to the 6th power, but D can't be negative, or else you're going to have a negative radicand with an even index. So you're just going to apply it that way. When you're taking out like this C to the 6th here, you're going to have to take out an absolute value of C, because you can't, if someone inputs a negative C, you can't have that outputting a negative C as well. But if someone can't input a negative D to begin with, so you don't have to worry about the absolute value on the D. So you would have, this would be, let's see, 64 is 16 times 4, which is 4 times 4 times 4, 2 times 2 times 2 times 2 times 2 times 2. So 2 to the 6th is 64, so we have a 2 absolute value of C, and then this is D to the 6th times D cubed. So we just have a D. We don't need the absolute value, and you're left with this. Okay? So that's the idea of dealing with these absolute values in that are coming out of these even index radicals. Now, if the index is odd, it doesn't. Then there's no. Just do it like you normally would do it. You don't have to think about absolute values. Just do it like you normally would do it. Just separate them out this way, and then here you take out. So you're like, you could take out an x here, and then you're left with, but just don't put the absolute values. Okay, now this is a good time to look at the point number 4 here. Because if you, okay, we've got these 2 forms right here. Are these simplified? Well, according to point number 4, they're not. So why not? So this says the exponents in the radicand may not all share a common factor with the index. So what they're talking about here is that this is going to be very clear to illustrate if we convert this to the exponent form. So x squared times, okay, so we know this would be, right? Well, look, there you go. You see why it's not simplified? You can, that's not a reduced fraction. So this is, in reality, this is x squared root x. Same idea here. This should be, so d to the 3/6, that's d to the 1/2. So now it's fully simplified. But if you had something like, well, this you can't simplify any further. Like 3/8 is fully reduced. Okay, so now what about points 2 and 3? These are related to fractions. So point 2 is just saying that it's not simplified if you have a fraction inside of the radicand. So here we have a fraction inside of the radicand, so it's not fully simplified. So we want to apply the quotient property so we can put the radical in the numerator and denominator. Okay, now let's see. We've got, so the principal square root of x squared, is this going to be the absolute value of x? Well, we come back to the original problem and we see that, yes, we can have input negative x values. So we will need to say this. Okay, now is this fully simplified? Well, no, it's not, because of point 3 here. You can't have a, it's not fully simplified if you have a radical in the denominator of a fraction. So to fix this, we want to rationalize the denominator. So we'll multiply by root 6 over 6, and we're left with... Now, that's fully simplified. Okay, so if you have a fraction inside of a radical, just apply the quotient property and then go from there. Okay, now, when it comes to this rationalizing the denominator, note that this is simple when it comes to if you have a square root, you just multiply by 1 in the form of here, root 6 over root 6. But, okay, what if we had something like the... Okay, well, this isn't fully simplified because we have a radical in the denominator of a fraction. So do we just multiply by 1 in the form of the principal cube root of w squared over the principal cube root of w squared? Well, no, that's not going to work. It only works out this nice simple way with square roots because 1/2 plus 1/2 is equal to 1, right? Because it's like the idea is in the denominator here you have 6 to the 1/2 times 6 to the 1/2 is equal to 6. You get rid of any rational exponents in the denominator. So that's the goal here. What we're trying to do is we're trying to get rid of that rational exponent in the denominator. And so how do we do that? Well, we need these to add to 1, these exponents. So we want to multiply by w to the 1/3, or the cube root of just w. And we're going to get w over, and then we'd have... So that would be fully simplified. You see the difference? Okay, and so, yeah, there you go. There's a review of how you simplify radical expressions. Now, before we end the video, let's think about... Okay, so we've worked with simplifying expressions that contain rational exponents, but how are these kind of related to radical expressions? I mean, they're definitely related in some way. So, but how do we think about the difference? Because it's kind of weird to think about how it was really simple. Simplifying this was really simple comparatively to the radical expressions. Because we can treat rational exponents like any other exponent in terms of the exponent properties, and you simplify this all the way until you get to the end, until it's fully simplified, and you just leave it. And like there was no complications in the same way that we had a lot to consider when it came to radical expressions. So what's going on here? Well, okay. First of all, when we simplified these rational exponent expressions, okay, it's not like when we got to the end, it's not like we could, you might think that it seems like we could start with a radical expression. Let's say we started with this radical expression. So let's see, we'd have 3 root x over, okay, so we could potentially start with this radical expression, and the idea would be maybe we could just convert it to this, which we know we could, simplify it, and then convert it back to radicals and skip the whole process of ever having to deal with what we just learned about how to simplify radical expressions. Well, it's not going to work that way. You can't get around all of the complications that come with dealing with actual radical expressions, all those absolute values, etc. You can't get around that if you're going to use radicals. Yeah, if you actually never want to consider radicals, then I guess you could kind of think about doing that. But we worked examples, and actually in this case, it ends up being you can't actually skip dealing with radicals. In this is a special case of that because we've got 3 to the 4th times x to the 4 times 1/2, okay, y to the 3/8 times 4, okay, all right, 3 cubed. Okay, so now these cancel. Okay, and so we're left with 3 over x squared, and we're done there. There's actually no radicals mixed in here, so it actually does work out this way. to where we kind of skip dealing with radicals for this problem. But in general, it's not going to be that way. So, like, for example, let's say we had an expression like this and we got all the way to something like this. Well, we could leave it like this. You might think, no, there's a radical in the denominator, but no, not if you leave it like a rational exponent term. So we worked examples where we had something like this and we're asked to simplify, and so you want to get rid of those negative exponents. All right, and so, but we were done here. The textbook considered this fully simplified. You don't look at this, for the case of simplifying, you don't look at this like you have a radical in the denominator, even though you kind of, I guess technically you do. Okay, but you can see, though, that if you wanted to like switch everything to the rational exponent form and simplify and then try and switch back to radicals, you're still going to have to deal with simplifying radicals, because in this case you would do, you would have, okay, you converted, this is fully simplified, right, as far as the rational exponent form, but if you convert it back, then you've got, right, well, now we have a radical in the denominator, so we're not done then. So we've got w to the 2/3. So we want to do, let's see, w to the 1/3 over w to the 1/3. So we'll get, it's going to be 3 cube root of y cube root of w over w, and we can actually combine the y and the w. So you can see in radical form, this is fully simplified. Not, you can't just convert this to radical form and then you're done, even though this was fully simplified in the rational exponent form. And the same idea here. So this would be, well, we can see that this is obviously in radical form, this is not fully simplified, so we take out an x. Okay, but now we need to rationalize this, so we'd be what, x to the 2/3, and actually we probably shouldn't have, yeah, we should probably have started with rationalizing. So, okay, if we're going to convert this to radical form, then we, well, how do we do this? Yeah, I mean, we could start here. So, okay, well, so we can, in this case, we want this to add to, we can't get this to add to 1. We want to add to 2. So 4/3 plus 2/3 is going to be equal to 2. We just want to get a whole number in the exponent or an integer, so we can get that, so we don't have a radical. So 2/3 plus 4/3 is 6/3. So yeah, there we go. So we've got 3x to the 2/3 over x squared. So this is 3, and there we go. That's fully simplified in radical form. Okay, so that gives you a sense of the relation between the rational exponent simplifying problems and the radical problems. And it also gives you a sense of why it seemed like we were kind of being able to skip all of the complications that came with simplifying radicals. But in reality, a lot of times when we got to the fully simplified form, we just weren't going that extra. We were kind of leaving it, in relation to radicals, we were kind of leaving it unsimplified.